Okay, so in today's lecture, we will continue working on Newton's second law. Okay, so as a reminder, in order to solve any problem using Newton's second law, the first thing we do is we draw a free body diagram. That is, we put the object and we put all the forces acting on it. Second, we choose an x-axis along motion, then y-axis perpendicular to it. Then we apply Newton's second law, summation of fx equal ma, or summation of fy equal to 0. Here is just a reminder, if the object is at rest or moving with a constant speed, implies also summation of fx is equal to 0, because the acceleration will be 0 in this case. Okay, so let's do a simple exercise from your booklet. So the combined weight of the crate and dolly is 300 Newton. The man pulls on the rope with a constant force F equal 20 Newton. So what is he giving me in the given? First, W equal 300 Newton. The force F is equal 20 Newton. Okay. And he also tells me that it starts from rest. It starts from rest. It means V initial equal to 0. And there is no friction. So friction is 0. Okay. This is the given. Part A, find the acceleration of the system. So this is a problem where we cannot solve it using the previous kinematic equations. Summation of fx delta x equal v initial delta t plus half a delta t squared, because we don't have any information about the final delta x, delta t, nothing. So in order to find the acceleration, I have only one way, which is to solve summation of fx equal ma, because the acceleration, we will use summation of fx equal to ma. Before I start solving the problem, the first thing is we draw free body diagram. Okay, so to do free body diagram, the first step, because here there is a surface, we draw the surface. Then we put a tiny dot. Now we put the forces acting on it. The first force we always put is the weight. It's perpendicular to the ground. Then there is the normal perpendicular to the surface and away from it. Then there is this friction, then there is this tension force. He calls it F, so we have to call it F. So this is vector F, this is vector M, and this is vector W. I have to put the vector sign, all of them. Vector, vector, vector. Okay, these are the only forces. There is no friction, so there is nothing in the opposite direction. The second step is to choose x-axis and y-axis along motion. So it's the x-axis along motion. It's moving in that direction, right? It's moving in that direction. So the x-axis will be in that direction. The y-axis will be perpendicular to it. So the y-axis will be upward. So this is here. X-axis. And this is y-axis. Okay. Now, what is the acceleration? So summation of fx equal to ma. So I have three forces. So I have mx plus wx plus fx is equal to m times the acceleration, and x equal to 0 because n is all on y-axis. Wx is 0 because all of w is on the y-axis. Fx equal to F. This is equal mass times the acceleration. So acceleration is equal force divided by mass. Here, to get the mass, I have to remember that W is equal mass times gravity. So mass is equal W over gravity. So mass equal 300 divided by 10. Mass is equal to 30 kilograms. Okay, so I come here. Acceleration equal F, which is 20 divided by 30, and this is equal 0.66 meter per second square. Okay, so this is the acceleration. Part B, how far will the system move in 2 seconds? So part B, how far will the system go? So how far means it's asking for delta X. What information do I have? I have delta T, 2 seconds. I have the initial 0. I have acceleration 0.66. So in order to get delta X, I have to use the initial delta T plus half times A times delta T square. You just plug in the numbers and you get delta X equal 1.34 meters. Okay. This is solved fully in the coming slide. Before I move, yeah, so this is, let's move on. Yeah, this question is solved in the live session of today. So if you go to live session 11/11/21, you will find the solution to this problem again. So let's move on. So another force I want to illustrate. So now we know the weight is always perpendicular to the ground. It's equal to m times g. We know the normal is perpendicular to the surface. It's away from the surface. Okay. Today I will talk a bit about tension. So tension happens if I have a rope, if I have a string, if I have a rubber band, there is tension. Okay. Now the special case of tension is if I have a spring. This is a spring in its relaxed form. This is a spring in its relaxed form. It has some length L. If I attach some mass to it, it will get elongated. Okay, it will get elongated a certain distance delta L. The other option is to compress the spring. I compress the spring by also a distance delta L. Hooke's law for the magnitude of the T, it's equal to K. K is some spring constant. Okay, it will either be given or I have to calculate it. It's some spring constant, and delta L is how much it was elongated or how much it is compressed. Okay, this is called Hooke's law. Perhaps you remember it from grade 4, I think. What you have to know about the tension. So this is about the magnitude. It's equal K times delta L. What is its direction? Tension is a restoring force, which means it always wants to bring the spring back to its relaxed form. So in this case, it's elongated. It wants to bring it back to relaxed form, implies the tension will be upward. Okay. In this case, it's compressed. It wants to bring it to relaxed form, implies it will push it downward. Okay, so this is how we know the direction. If it's elongated, it's upward. If it is compressed, it's downward. Okay, also, if I have it in this way, it's not always, it can also be in this direction. It can also be like this, the spring. Okay, if this is the relaxed form and I elongate it, okay, this is here distance delta L, the red delta L, this is in red, the red part is delta L, and the direction will be backward because it wants to go back to relaxed form. Okay. Now let's solve 2 simple exercises to see how we deal with this. So a spring oriented vertically is attached to a horizontal surface as shown in the figure. The spring has a force constant. So here is the force constant K that appears in Hooke's law. How much is the spring compressed when an object of mass M is placed on top of it and the system is at rest? So the system is at rest implies acceleration equal to 0. Okay, it's at rest implies acceleration is equal to 0. So the first thing to do with this is a problem with forces. So the first thing I do the first thing I do is draw free body diagram, even if the question is not asking me. I cannot solve it without doing this. So I put my object, I put a dot, and I draw the forces acting on it. So there is always the weight. I never forget the weight. It's perpendicular to the ground. Okay. And then there is this spring which is compressed. So how will it be pulling or pushing? Will it be pushing the mass upward or pulling it downward? Will it be pushing it upward or pulling it downward? The spring is compressed. So it wants to go back to the normal length, elongation. So the tension will be upward. Okay, so this is W. This is tension. This is tension. It's a vector. It's a vector. Okay, so this is the object and I put the forces on it. There is no surface, so there is no normal. There is no surface, so there is no friction, and there is nothing else here. There's only the W and the tension. Now, this is the free body diagram. Then the next step always to choose x-axis along motion and y-axis perpendicular to it. So I come and I draw my x-axis, which was a different color. This is the x-axis. If it's moving upward because it is compressed. Once I remove my hand from so here I'm putting here the object is compressing the spring and it's at rest. But if it's moving, the spring will be pushing it upward. So I will choose the x-axis to be upward. To be honest, it doesn't matter if I choose it upward or downward because the object is at rest. So it doesn't really matter. Okay. The y-axis will be, if the x-axis is upward, the y-axis will be perpendicular to it and counterclockwise. عكس عقارب الساعة. Okay, counterclockwise. But if there is no need for the y-axis because everything on the x-axis, but it's okay. Let's keep it. Now I have to choose whether I will use the same first formula or second formula. Let's see what the question is asking for. How much is the spring compressed when an object of mass m, so I have the mass m equal to 0.3 is on top of it. So the question is about how much is the spring compressed. So it's asking me about delta L. Okay, so I use the formula tension equal K delta L. Tension, I don't know how much is it, equal K, I know it's 1.46 Newton per meter, so I don't have to worry about the units are correct, times delta L, which also I don't know. What can I find? I can find the tension using, summation of using Newton's second law. Using Newton's second law, which is summation of Fx equal to 0 because the object is at rest. Summation of Fx is Tx plus Wx is equal to 0. Tx is all of t because it's along the x-axis and it's plus, so it's a plus t. Wx is all of it is along the x-axis, so this is the x-axis. W is along the x-axis, but it's in the opposite direction, so it's minus W is equal to 0. So T is equal to W. T is equal M times G. T is equal 2.3 times 10. T is equal 23 Newton. Okay. Now we go back to the original question. T equal K delta L. So delta L is equal T over K delta L is equal T 23 divided by K, which is 1.46. Delta L is equal to 15.75. Okay, so the important thing here, let me repeat the important part. The important thing here is drawing the free body diagram and applying the forces. So let me do it again. Here, to draw the free body diagram, I only have the object. So I put instead of it a point. Okay, there is no surface, so I don't draw a surface. There is weight, we're acting on it. And there is tension upward. Why there is tension upward? Because the spring is compressed. The spring is compressed, so the spring wants to go back upward. So it pushes upward. It's pushing upward. Okay, so this is tension, this is weight, and this is tension. And these are vectors, so this is tension and this is weight. Then I have to choose the x-axis along the line of motion. So it's either moving upward or down. It's actually at rest, okay? But if it will move, it will either move upward or downward. So I chose upward to be x-axis. So my x-axis is upward. Okay, and then how did I solve it? I solved it using summation of fx equal to 0 because acceleration equal to 0 because the object is at rest. I have tension is along the positive x-axis, all of it on the x-axis, so tx is plus t. W is also on the x-axis, but in the negative direction, so it's minus w, and I solved it to find tension. Then from the tension, I got delta. Let's do another exercise with the springs. So you find the full solution here, okay? A block of mass M equals 0.46. So I have the mass attached to a spring with force constant K. So I have this K is free to move on a frictionless, so there is no friction. The block is released from rest after the spring is stretched a distance A equals 0.13. So the spring was here originally. It was here, okay? But they elongated it and then they left it. At point A, so when the object was at point A, find the tension force, okay? To find the tension force, I try to use Hooke's law. So using Hooke's law, can I do it using Hooke's law? If yes, then I'm done. Tension equal K times delta L. Tension equal K is given 130 Newton times delta L is given. Here they called it A, it's no problem. So 0.13. So tension is equal to 16.9 Newton. So I got the tension. This is part A. Part B, find the acceleration. So in order to find the acceleration, I have to use summation of fx is equal to m times acceleration. That's where there is acceleration, right? If I use summation of fy equal to 0, there is no acceleration. But summation of fx equal to ma, then I can get the acceleration. So I have to get the forces and to get its summation. So first I have to draw free body diagram. Here there is a surface, so I have to draw the surface. Okay, and I have to put my object on the surface. And now I have to draw the forces. So there is the force weight downward. It's perpendicular to the ground, okay? And normal perpendicular to the surface. And there is a spring, okay? It wants to bring the spring back to the original place. So the pushing or the pulling in this case, it's in this direction. So the tension is in this direction. And there is no other force. There is no friction. There is no other force. So this is normal force. This is W force. And this is tension force. And they are vectors. So I have to put a vector. Okay. So this is the first step. I draw the free body diagram. The second step, I choose x-axis along motion. So this mass, how is it moving? It's moving in this way. So I choose the x-axis. Let me choose another color. The x-axis is in this way. And the y-axis is perpendicular to it and counterclockwise. Okay, so this is here. X-axis, this is here. Y-axis. Now summation of fx equal to ma. So I have tx plus wx plus nx is equal to mass times a. Tx is all of t, and it is in the positive x-axis, so it is a plus t. Wx is 0 because w is along the y-axis, so it's plus 0. Plus nx is also 0 because it's along the y-axis. This is equal m times a. So acceleration is equal t divided by m. Acceleration is equal t is 16.9 divided by m, it's 0.6 given. Acceleration equal 28.16 meter per second. Okay, so this is all for today's lecture. If you have any questions, just send me an email and I will talk about it in the coming live session. Bye-bye and have a good week.